professor in chemistry at Arts and Science College, Rishabh. So today's topic about presentation is from the B.Sc third year, Unit 4, Section A, Dyes. Okay, this Unit 4 is divided into three sections. Section A is dyes, Section B is drug, and Section C is pesticides. Out of these three sections, today we are going to discuss Section A, that is dyes. Okay, let's begin with the dyes. So in the introduction, dyes are nothing but the colored organic compounds. Okay, these colored organic compounds are used to color various other things like paper, leather, fur, hair, drugs, cosmetics, packs, grease, etc. Okay, so dyes are nothing but what? It is a colored compound. Okay, normally it is used in a solution which is capable of being colored, being fixed to fabric. This dyes has the property to fix to the fabrics of the clothes. Okay, so colored organic compounds must possess two groups, chromophoric group and oxochromic group, to become a dye. Okay, without these two groups, the colored organic compound can't be a dye. Okay, so these two groups must have to be present in the compound so that it can be used as a dye. Okay, so what is chromophoric and oxochromic group? Chromophoric group is the group which is responsible for the color of the compound. Okay, why this chromophore is only responsible for the color of the compound? Because it is capable of absorbing the UV light. Okay, it absorbs the UV light and we see the color to that particular compounds. Okay, so the compounds which shows the presence of this chromophore in their structures, such compounds are known as chromogens. What they are called as? They are called as chromogens because chromophoric group is present in those compounds. Okay, so example of chromophores are NO2, that is nitro, N double bond O, that is nitroso, N double bond N, that is azo, C double bond O, that is carbonyl, C double bond S, that is thiocarbonyl, C triple bond N, that is cyano group, etc. These type of groups, if are present in a compound which are color compound, then such compounds are known as chromogens. And all these group whatever we have seen, like nitro, nitroso, azo, carbonyl, thiocarbonyl, cyanide, etc. groups are nothing but the chromophores. Okay, so the whole compound is called as chromogen, and these groups are called as chromophore. Because of presence of these groups, it shows the capacity of absorbing near the UV light. Okay, so this is all about the chromophore. Now we'll see oxochrome. What is oxochrome? Look what happens. Dyes gets attached to the fiber. Okay, so something must have to be there between the, or some force of attraction must have to be there between the dyes, and that is the color compound, and the material to which this dye is going to attach, that is fiber of the cloth. Okay, so this attraction or these bonds are formed by presence of acidic or basic groups in the colored compound. Okay, so these groups are known as oxochrome. Okay, this acidic or basic group which are present in a chemical compound, so that it gets attached to the so that it is get attached to the fiber or the cloth. So these groups are called as oxochromes. Okay, there are two types of oxochrome: acidic oxochrome and basic oxochrome. So example of acidic oxochrome are OH, that is hydroxyl, COH, that is carboxylic, and SO3H, that is phenylic group. Okay, sulfonilic acid group, sorry, not phenylic, sulfonilic acid group. Okay, so if these groups are present as an oxochrome in any dye, then such groups are called as oxochrome, acidic oxochrome, right? Then primary amine, secondary amine, tertiary amine comes under the class basic oxochrome. Okay, now next we are going to see the definition of the dyes. Okay, so dyes are the colored substances capable of being fixed to fabrics like silk, wool, cotton, and other substances like paper, leather, and when fixed dyes must be fast to light and resistant to the action of water, dilute acids, alkali solutions and bleaching. So this is the definition of the dyes. Okay, mug up this. I can say anything about this definition. So you have to mug up this definition. Okay. So commonly, now after the definition, commonly the dyes are classified into two classes depending on the source from which these dyes are obtained or made. Okay, so the classification is like natural dyes and synthetic dyes. So natural dyes, yes, we can say the source from which these dyes are made are the natural ones like plants, animals or minerals. Okay, so naturally these color compounds are obtained in plants, animals and minerals. So from there these compounds are obtained and used as a dye. So they are made from the natural sources. So these dyes are called as natural dyes. On the other hand, synthetic dyes are the dyes which we are seeing today are almost synthetic dyes because they are synthesized in the laboratory. Okay, so they are called as synthetic dyes. And in the natural dyes, majority of the natural dyes are vegetable dyes from plant sources. Okay, so majority of the natural dyes which we are using today or using as a dyes are obtained from the plant sources like roots of the plants, like berries, fruits, barks, leaves and woods. So this type of material is used as a natural dye to color the fiber. And the other organic sources in the natural dyes includes fungi and lichens. Okay, so lichens are the what we can say, a class of plants. Okay, so it is a kingdom of the plant, maybe a kingdom of plant, but lichen is a plant. Okay, so you might be knowing the masala that we are using in our day-to-day life, the dagadful. So that is nothing but the lichen. Okay, now in the synthetic dyes that which we are used today to dye clothes, foods, boots, okay, everything which we see color today are colors of the synthetic dyes. Okay, why the synthetic dyes are introduced? Because they are very cheap to produce. Okay, and these are very brighter, these are more color fast and easy to apply to the fabric. So that's why synthetic dyes were introduced or discovered. Okay, and used in day-to-day life very much. Okay, so example of this synthetic dyes are acidic dyes, azo dyes, basic dyes and modern dye, etc. So these synthetic dyes we are going to discuss in details in the coming slides. Okay, so don't worry about this, what is this acidic dyes, azo dyes, basic dyes, modern dyes, we are going to see it. Okay, next. Now natural classification, that is the classification on the basis of the source of the dye we have seen. Okay, now next classification is done on the basis of 1, structure, 2, the mode of application and 3, the acidic and the basic nature of the oxochrome present in the dye. Okay, so out of this first we will see the classification depending on the structure is again divided into or again classified into the main types. One of first is nitro or nitroso dye. Okay, so these are the structural features of this dye. Nitro or nitroso, the dye contains nitro group or nitroso group in it. Its structure are called as, it comes under this class. Okay, or are called as nitro or nitroso dyes. Azo dyes means the dyes in which the structure shows as presence of azo group in it. Okay, then triphenyl methane group the same. If triphenyl methane group is present in the structure of the dye, then that dye comes under this class. Then phthalate dyes, if the phthalate group is present in the structure of the dye, then that dye comes under the class phthalate dye. Then indigoid or thioindigoid dye, again the same thing. If those groups shows this indigoid or thioindigoid groups in it, structure shows it. If the structures of the dye shows indigoid or thioindigoid structures in it, or the groups in it, or functional groups in it, then this comes under the class thioindigoid or indigoid dyes. Then anthraquinone dyes. If anthraquinone is present in the structure of the dye, then that comes under this class, anthraquinone dye. Then in miscellaneous dyes, azine dyes, sulfur dyes, xanthine dyes, phthalocyanine dyes, etc. comes under. Okay, so these dyes are not belonging to upper 6 dyes, so they comes under the class miscellaneous dyes. Okay, this is particularly mix up all others, right? These dyes we can classify like nitro, nitroso, triphenyl, methane, methylene dyes, indigo, thiindigo dyes, and anthraquinone dyes. But these azine, sulfur dyes, xanthine dyes, we can classify them into the groups, so we take it under the miscellaneous dyes. Okay, then we will see the nitro and nitroso dyes. This is the picric acid. It contains the nitro group. Okay, 3 nitro groups in it, so it is the nitro dye. Again, the naphthol LOS, it also shows the presence of the nitro group, so it comes under the class nitro nitroso dye. Then again, the Marcius yellow, it shows the presence of the nitro group, so it comes under the nitro and nitroso dye. Again, this naphthol green Y, it shows the presence of the nitroso group, N double bond O. Okay, here N double bond O. So this group is called as nitroso group, and this comes under the class nitro and nitroso dye. Okay, so what are these dyes? These dyes are polynitro. Polynitro means more than 1 nitro group present. Here 3 nitro group present, here 2 nitro group present, here also 2 nitro group. Polynitro. Okay, nitro groups more than 1. So here all these 3 dyes shows the polynitro derivative of phenol. This aromatic ring attached to OH, okay, or this OH group attached to the aromatic ring is phenol. Okay, and these are the 2 aromatic rings, okay, attached to one another, and to these 2 aromatic rings one OH group is present, and such group is called as naphthols. Okay, so the polynitro derivative of phenols and naphthols, in which one of the nitro group is either present ortho or para to the hydroxyl group, where ortho to the hydroxyl group or para to the hydroxyl group. Okay, this is the speciality of this dyes. Okay, in these dyes, this nitro group should be present ortho or para to the hydroxyl group. Okay, so if we draw the canonical structures, okay, the canonical structures means the resonating structures, then we'll see this the formation of the double bonds, that is this is the electron donating group and this is the withdrawing group. So the number of structures we will get more, okay, on drawing the canonical structures of the resonance structure. So because of this resonance structure, it absorbs the light and it produces or gives the color. Okay, so because of this, the color to these compounds occurs. Okay, then this again, the next specialty of these dyes are, these are industrially less important, as these dyes are not fast. Okay, these dyes are not fast, so industrially they are less important, because in today's competition, if you want to become a dye, that dye should be fast to light, fast to soak up, fast to get attached to the fiber. So this is not fast in all those particular things, so this is industrially less important. Okay, then naphthol yellow S, this dye is used in edible material, okay, to color the edible material. What is edible material? The material which we consume, okay, as a food. So there, this naphthol yellow is used as a coloring agent. It colors yellow. Okay, all these 3 structures shown in yellow gives yellow color, and this structure, this naphthol green Y, gives green color, so it is shown in green color, right? Then next class of dyes is azo dyes. Okay, it contains one or more azo group, N double bond N group, as a chromophore in it. Okay, and oxochromes can be OH group, SO3H group. These 2 are the examples of the acidic oxochrome, and NH2, NR2, that is primary amine, secondary amine, are the oxochromes in it. Okay, so N double bond N is chromophore, and these other groups are oxochrome. Okay, these dyes possess wide range of colors ranging from yellow to orange and red. Okay, this dye shows wide range of colors ranging from yellow to orange and red. Okay, then preparation of these dyes. Okay, we'll see the preparation of these dyes. This aniline on diazotization gives this diazo salt, okay, this diazo salt, and this diazo salt on diazotization or reaction with the aromatic phenol or amine produces this azo dye. Okay, and examples of azo dye are methyl orange, Congo red, para red, Bismarck brown, etc. Out of these examples, methyl orange we are going to see in details their preparation and uses and properties. Okay, so this is the structure of the methyl orange. Okay, so it shows this N double bond N chromophoric group, that is azo group, and SO3H is the acidic oxo group. Okay, so this is the acidic dye. Look here, this is the acidic dye because of this SO3H acidic oxo group. Okay, and as this is acidic group, it is very much soluble in water, right? So now its IUPAC name is that is International Union of Pure and Applied Chemistry is the short form or is the full form of the IUPAC. Okay, so name of IUPAC name of this methyl orange is 4,4-dimethyl amino phenyl diazenyl benzene sulfonic acid. Okay, benzene sulfonic acid. This is the IUPAC name of this methyl orange. Now how to prepare the methyl orange? Okay, so methyl orange is prepared in two steps. First is diazotization of sulfonylic acid. Okay, diazotization of sulfonylic acid. Before this diazotization, we are going to see a reaction in which this HNO2, that is nitrous acid, is produced. What happens? The NaNO2, okay, is reacts with HCl to produce HNO2 plus NaCl, and this HNO2 is used in the next reaction, that is diazotization reaction of the sulfonylic acid, and this HNO2 is nothing but the nitrous acid, HNO2. Okay, the sulfonylic acid, okay, this sulfonylic acid is reacts with this nitrous acid in presence of HCl at 0 to 5 degrees Celsius, produces this diazotized sulfonylic acid salt. Okay, this diazotized sulfonylic acid salt. Okay, and this process is known as diazotization. Okay, formation of N double bond is nothing there but the process diazotization. Okay, now this diazotized sulfonylic acid is further reacts with aniline here. Okay, dimethyl dimethyl aniline. Okay, here phenol also can be used, but in this particular reaction we are going to see the reaction of this N-dimethyl aniline with diazotized sulfonylic acid salt in presence of NaOH produces a sodium salt of methyl orange. Okay, so it produces a sodium salt of methyl orange. This is shown in orange color because it produces or gives the orange color to the fiber. Okay, now properties of this properties of this methyl orange. Yes, so water soluble because acidic SO3 group is present, that is we have seen. It is not sufficiently fast to light and soap. Okay, then next is generally it is isolated as a sodium salt, as we have seen. Then it gives orange color to the wool and silk, that is fiber. We have seen that too. Okay, it is used as an indicator in acid alkali titration. Okay, this is the most important point. It is used as an indicator in acid alkali titration. Okay, it gives orange color in alkaline solution and gets red in acidic solution. Okay, so this is the use of the methyl orange most commonly. Okay, you have also seen the bottle of this dye in our lab too, right? Now the next class is triphenyl methane dye. Okay, triphenyl methane dye. So this is the structure of triphenyl methane skeleton. Okay, so that dyes which contain this skeleton comes under this class, that is triphenyl methane dyes. Okay, here the spelling mistake is there. Methane should be written like this. Okay, now what happened? So we are going to see some details about the structure. The central carbon atom is attached to 3 aromatic rings. Okay, the central carbon atom is attached to 1, 2 and 3 aromatic rings. of these three aromatic rings, one is quinoid structure, okay, one is para-quinoid ring, another two are benzene rings. These two are benzene ring and this is the para-quinoid, okay. So this is the structural peculiarity about these triphenyl methane dyes. Now these dyes are shows quinoid group as a chromophore, okay, quinoid group as a chromophore, have intense color but fade rapidly in light, means they are having intense color, but when you keep this dye in light, that color gets faded away, okay, it gets faded away. पहले dark असतो नंतर थोड़ा थोड़ा कमी कमी होत जातो. This is how firstly it is very intense and it gets fade away in light, okay. So not used in textile industry. So this is having the limitation that you can put it into light as it reduces its color intensity. So it is not industrially used in textile industry, right? So it is used to color papers, typewriter ribbons, okay, so etc. Here it is used as a dye. So example of this particular class are crystal violet, malachite green, rose aniline, that is magenta, para-rose aniline, methyl violet, aniline blue, etc. Out of this example, crystal violet, we are going to see in bit detail about its preparation and uses. So this is the structure of the crystal violet, which is shown in violet color, okay. What is the structural peculiarity of this structure? Two aromatic ring which are having two methyl group attached to the aniline group, okay. Aromatic anilines, these are the aromatic anilines, dimethyl aniline. So these two groups are the dimethyl aniline groups and it is attached to the quinoid structure, right. So this is the crystal violet, okay. Now its preparation, first step is preparation of Micheler's ketone, okay. And what happens in Micheler's ketones? This dimethyl aniline, one of this unit, dimethyl aniline reacts with carbonyl chloride, that is COCl2. It reacts with carbonyl chloride and it gives away this HCl and this gets attached to this carbonyl group two times, okay. First this HCl, again this HCl. So two HCl molecules are going away and two dimethyl aniline groups attached to this carbonyl group like this, and this compound is nothing but the Micheler's ketone, okay. Now again condensation of, next step is condensation of Micheler's ketone with dimethyl aniline, okay. Again now what happens, this Micheler's ketone is again reacted with dimethyl aniline in presence of anhydrous POCl3, okay, and this reaction is condensation, okay. What happens over here, this ring gets attached to this carbonyl group and this becomes OH, okay, like this. Now what happens, the double bond on the nitrogen shifted into this carbon nitrogen bond, this double bond gets shifted into this single bond over here, this double bond gets shifted over here between this carbon and this OH2 gets away along with the POCl2 and the HCl is get liberated over here, okay. So this is how minus POCl2 and minus HCl gives this crystal violet, right. Now what are the properties of crystal violet? Large violet color crystals, okay. This compound is crystalline in nature, which produces large crystals which are violet in color, okay. It is soluble in water because of presence of this salt in nature, N plus Cl minus, so it gets dissolved in water and it gives deep blue color, okay. It gives which color? Deep blue color, okay. Where it is used? It is used to dye wool, silk and cotton fibers, okay. Now what are the uses of crystal violet? It is used in pencil making, it is used as a biological stain to stain the cells in microbiology, it is used as an antiseptic for skin, okay. It is used as an antiseptic for skin, so it has medicinal use also. Gentian violet, that's crystal violet plus methyl violet, used as an indicator in acid alkali titration, okay. So this is chemical use of this gentian violet, which is a mixture of crystal violet and the methyl violet. So in manufacturing of ink, stamping pads and typewriter ribbons, here also this crystal violet is used. Now the next is phthalate dyes, okay. The next class is phthalate dyes. So these dyes are formed from phthalic anhydride and phenols in the presence of dehydrating agent like fused ZnCl2 or concentrated H2SO4. This concentrated H2SO4 and fused zinc chloride are used as a dehydrating agent. Okay, so this phthalene dye again shows the presence of the triphenyl methyl group in its structure like the previous one. Okay, an example of this phthalene dye is phenolphthalein, which is mostly used in titration, acid base titration, right? Use colorless to pink color, right? So this is the structure of the phthalene dye. Okay, so this is nothing but the phthalene group, anhydride, phthalic anhydride group, right? So again, its preparation we are going to see in details. What happened? This 2 moles of the phenol reacts with the phthalic anhydride in presence of the dehydrating agent, that is concentrated H2SO4. What are dehydrating agents? Which dehydrating agents are those agents which are used to remove the water molecule from the compound. So here dehydrating agent is concentrated H2SO4 to produce this phenolphthalein. In one step reaction, 2 moles of phenol reacts with the 1 mole of phthalic anhydride in presence of concentrated H2SO4 gives the phenolphthalein indicator, okay, of the phenolphthalein dye. Okay, now properties: white crystalline solid. It is white crystalline solid, insoluble in water but soluble in alcohol and alkali, right? It is insoluble in water. As phenol structure is there, it is insoluble in water, right? Phenols are insoluble in water, right? Yes. Again, so insoluble in water but soluble in alkali, alcohol and alkali. Okay, what are the uses of these phenolphthalein? It is used as an acid base indicator than a dye. Okay, so most common use of this is the acid base indicator. It gives pink color in alkali and colorless in acid. So we have seen this pink color. Okay, then next class is indigoid and thioindigoid dyes. Okay, these dyes contains C double bond O, C double bond C, C double bond O, C chromophoric group. Okay, so this type of structure is present in the structure of the dye. These dyes should come under the class indigoid or thioindigoid dye. So example of this is indigo dye. So it is now this something about this indigoid dyes. These are obtained from plants. Okay, these are obtained from plants. It is dark blue amorphous powder with copper luster. Copper means tamba surface, right? So that type of luster it have. Okay, then used as a dye to color cotton on large scale. It gives dark blue color to the fiber, okay, of the cloth, and extremely fast to washing. So it is industrially very important, and it is a natural dye. Okay, because it is obtained from plants. Okay, synthetically also it can be prepared, but it can comes under the class of natural dyes. Okay, so this natural dye is nothing but the jala, charbundwala, neem, right? So this is the neem, but the indigo dye in English, right? Now thioindigo dyes. What are the specialty of thioindigo dyes? It is similar in structure to the indigo dye, just instead of this nitrogen in the indigo dye, sulfur is present. Okay, NH2 group is replaced at this 2 position by sulfur group in the thioindigo dye. Rest of the things are same, and these are used to dye cotton, wool and polyester. Now preparation of the indigo dye. Okay, preparation from indigo plant. Okay, so this is indigon. This is the structure of the indigon. This is the indole to which this O6C6H12O5 group is attached. So this is known as indigon, which is obtained from the indigo plant. Okay, this gets hydrolyzed to hydroxyindole. 1, 2, 3 to hydroxyindole. This indole on oxidation produces the indigo dye. Okay, this indole on oxidation produces the indigo dye naturally, right? Next, this is the natural synthesis. Now the chemical synthesis. Anthranic acid. This is 2-amino-benzoic acid, or the anthranic acid, 2-carboxyaniline anthranic acid reacts with Cl, CH2, COOH. Okay, Cl gets removed, H from this and Cl from this group gets removed to give this compound. Okay, COH over here and one H from the NH2 is here, one H from this NH2 went silent with this Cl of this group, and this group directly gets attached to the nitrogen. Okay, now this compound in presence of KOH and NH2 soda amide and heat and dehydration gives this 1 carboxy 2 hydroxy indole. Again this 2 hydroxy 1 carboxy indole gets decarboxylized. Okay, on decarboxylation produces this indoxyl. Okay, this is the structure of the indoxyl. Okay, this indoxyl on treating with oxygen or on putting it in air gives this indigo dye. Okay, the next class of the dye is anthraquinone dyes. Okay, this include hydroxy or NHR derivative of anthraquinone. Okay, the paraquinoid chromophore is present in these anthraquinone dyes. Okay, quinoid is present. An example of it is alizarin. Now the structure of this is in the next slide. Okay, the alizarin obtained from the roots of the madder plant. Okay, search the image of the madder plant on the internet. So this is the structure of the alizarin, and this is nothing but the paraquinoid structure. 2 carbonyl groups present para to one another. Okay, so this is the paraquinoid. This hydroxyl group should not be there, and this structure is known as the quinoid structure, paraquinoid structure. Okay, and this hydroxyl group, if two these hydroxyl group are present, it is the alizarin dye. Okay, now preparation of alizarin dye. First step is the preparation of anthraquinone. Okay, this phthalic anhydride reacts with the benzene in presence of AlCl3. Heating, this triangle symbol means heating, produces this compound. Okay, this compound on again heating in presence of concentrated H2SO4, that is dehydrating agent. minus H2 goes away, one hydrogen from this position of the carbon and the OH group from this, and this directly get attached to this carbonyl group of this COH group to produces the anthraquinone. Okay, the next step is the sulfonation of this anthraquinone. Okay, sulfonation of this anthraquinone. Okay, this anthraquinone from the previous step, when treated with fuming H2SO4 and heated at 160 degrees Celsius, it produces anthraquinone sulfonilic acid. Sulfonation over this position is occur by using this fuming H2SO4 at 160 degrees Celsius. Okay, the anthraquinone sulfonic acid again next is converted to alizarin by using sodium hydroxide KClO3 fused and in presence of acid. Okay, so this anthraquinone sulfonic acid gets converted to the alizarin dye. Okay, this SO3H group is replaced by OH and one OH group is introduced over here by using these reagents to produce this alizarin from anthraquinone sulfonic acid. Now the properties of this alizarin is it produces a ruby red crystal of melting point 290 degrees Celsius. The melting point of the ruby red crystals of the alizarin is 290 degrees Celsius. Okay, it is sparingly soluble in water, means somewhat gets soluble in water, but it is more soluble in alcohol and ether. Okay, it dissolves in alkalis and gives violet to purple color salt, that is alizarate. Okay, and it is sublimate on heating. What is sublimation? When you heat some compound, solid compound, it should get converted to liquid, and then if you continue the heating, that liquid gets converts to vapors. But in sublimation, what happens? The solids directly gets converted into the vapors. So the process is called sublimation, and this alizarin undergoes the process of sublimation on heating. Okay, and it is a modern dye. Okay, that is, it forms colored salt with metallic oxides. Okay, if the dye forms the colored salt with the metal oxides, such dyes are called as modern dyes. Okay, so it gives red with aluminium and gives violet color when we treated with the Fe3 plus ions. Okay, when this metallic oxides are used of aluminum ion, it shows red color when treated with the oxide or metallic oxide of the aluminum, and used violet color when treated with the oxides of the iron. Right? What are the uses of the alizarin? Alizarin is used to dye cotton and wool. Okay, it is used to dye cotton and wool. It is used as a purgative in the medicine. So what is purgative? You have to tell me in the by searching. Okay, then it is used in manufacturing printing inks. Okay, so whatever the inks are present in printing presses, they can be manufactured by using the alizarin. Okay, the next classification of the dyes on the basis of its mode of application. And yes, we have seen the structure. Now on the basis of the mode of application. So there are 5 types. One is direct dyes or substantial dyes. Second is indirect, adjective or modern dyes. Third is ingrained dyes. Fourth is bright dyes, and fifth is dispersed dyes or the reactive dyes. So out of which first is direct or substantive dyes. Okay, so these dyes can be applied to fabric by direct immersion of the fiber into the aqueous solution of the dye. Okay, then it contains acidic or basic group which reacts with the acidic or the basic group on the fiber, so that it gets attached to one another. It is used to dye wool and silk. Okay, then example of this direct or substantial dyes are Marcius yellow, has acidic OH group, and which reacts with the basic NH2 group of the wool and the silk. Okay, so the reaction given over here is the NH2 group of the wool and silk, that is the fiber, it gets attached to the OH group of the dye, and the color is transferred from the dye to the fiber. Okay, like this. Okay, the bond between the OH and the NH. Okay, O and N के बीच में bond है. The next is the indirect or the mordant dye. Okay, indirect or the mordant dye. The name itself suggests are applied to the fabric with the help of salts like oxides of aluminum or chromium, and called as mordant. Such salts of metal are called as mordants. Okay, so the name is mordant dye, that is indirect dye. Fiber is treated with the mordant first, this is the oxides, and then to the solution of the dye, so that the fiber should get color. Then mordant forms an insoluble coordination complex between the fiber and the dye. Okay, so what is the role of the mordant? From one end it gets attached to the fiber, and from other end it gets attached to the dye, and this complex is formed. Okay, these complexes appears in the form of legs. Whatever those complexes are formed, those are formed in the form of legs, and that are very fast to light and washing, so it has an industrial application. Okay, example is alizarin. Okay, we have seen when it is attached to aluminum it produces red color, and when it is attached to iron it produces oxide of the iron, it produces violet color, right? Black violet color. So we have seen it, right? So the alizarin is the example of the indirect or the mordant dye. Okay, because this dye produces colors on its attachment to the metal oxides of the metals. Okay, oxides of the metals, and these oxides of the metal salts are nothing but the mordant. So this type of dyes comes under the class mordant dyes. Then ingrained dyes, that is azoic dyes, okay, are called as developed dyes. Okay, are called as developed dyes as the chemical reaction result in the formation of the dye with the fabric. Okay, it produces fast color, and these are water soluble. So the example of ingrained dyes is ingrained dyes. Okay, what is the procedure of drying? The cloth is first soaked in the alkaline solution of butanol and then dried. Then this dried and soaked cloth is dipped in a cold solution of the diazotized amine, and this diazotized amine kept the reaction between the diazotized and the naphthol soaked pre-soaked cloth occurs and produces the colors. If you directly put the cloth in the solution of the diazotase amine, it won't give color to the cloth. Okay, so first you have to soak the cloth in the alkaline solution of beta naphtha, and then you have to dry it. In this dried soaked cloth is dipped into the solution of the diazotase amine so that the fiber gets color. Okay, next class is wet dyes. Okay, so these dyes are on reduction with sodium hydrosulfate in the vat forms a colorless soluble compound which has a great affinity for cotton and other cellulosic thread. Okay, so we are going to see how this happens. Okay, in the form of reaction. This is the indigo dye. Okay, this double bond is there. This double bond on reduction gets converted into the single bond, and this double bond also gets converted into the single bonds, and double bonds gets appear over here and here. Then and then only this indigo blue gives color. Okay, indigo blue, when indigo blue gets color, this is the compound. Okay, when this compound gets oxidized, indigo blue color occurs. When this indigo blue color is again reduced, it gives a colorless compound. Okay, on reduction colorless, and on oxidation becomes color. So what happens in the procedure of dyeing? Cloth is soaked in a reduced dye solution. Okay, dye is present, and then sodium hydrogen. Okay, first what we have to do, we have to make the solution of this reduced dye. Okay, and then in this dye, cloth is soaked. Okay, then this soaked cloth is oxidized. Okay, oxidized with oxidant or air, and what happens then? This soluble form gets insoluble and produces the crystalline indigo colored onto the dye. So there, indigo dye is the example of the white dyes. What happens over here? This reduced form of dye, that is the solution of dye, and the sodium hydrosulfate is prepared in a container. In that container you have to soak the cloth, and this soaked cloth you have to oxidize with the help of the any oxidant, or you just have to keep it into the air for soaking, and the indigo blue color is produced onto the cloth. Okay, so this is solid, you can't rub the cloth onto the solid, so you have to make the solution, and for making the solution you have to reduce this compound to this indigo white. Okay, this compound is called as indigo white, which is colorless. Now into this colorless solution you have to put your cloth, and then this cloth you have to oxidize by using air or any oxidant, so that the indigo blue which is present over here in colorless becomes solidified to give the indigo blue color. Okay, so this is how the wet dyes works. Now the fifth type of the classification is dispersed dyes. Okay, or the reactive dyes. These are insoluble in water but gets dispersed in a colloidal form in a water. Okay, so colloidal forms like clumps. If you put a drop of water into the a drop of oil into the water, it forms a invisible type of thing. Okay, so this type of thing are nothing but the colloidal form. Okay, colloidal form. Now the fine dye particles gets absorbed into the crystal structure of the fiber. Fiber should have the crystal structure. Okay, this colloidal form gets absorbed by the crystal structure of the fibers on dispersion in the colloidal solution. What happens? Here you have to put the dye into the water, it forms a colloidal form, and then that colloidal form formed in a solution, and into that colloidal formed solution or the colloidal solution you have to put your fiber. Okay, so fiber has a crystal structure also as it is solid, and into that solid the dye particles gets absorbed. Okay, so this is how this dyes works. Okay, and it is used to dye modern fibers like nylon, orlan, polyester, and cellulose acetate. An example of these are nitro dyes, azo dyes, and anthraquinone dyes. So this is the nitro dye. Okay, this is again the example of the azo dye, nitro plus azo dye, and the anthraquinone dye. These are the para-anthraquinone, right? Selenium fast and selenium fast blue B iso plus nitro. Okay, iso plus